This is Daniel Keysbury, and in this video, we're going to look a little bit more about how to talk about the spread of a data set. So I recorded a video on ways to measure the spread of a data set, talking about standard deviation and variance. And so if you haven't seen that, watch that first, because we're going to use those ideas a little bit more to talk about the data set and just kind of describe it overall. I'm using things like the empirical rule and Chebyshev's inequality and the coefficient of variations. Let's go ahead and look at the empirical rule first. The empirical rule is really nice and it's really commonly used. If you end up with data that looks mostly bell-shaped, then you are allowed to use what's called the empirical rule. So if I've got a histogram and it's not only symmetric, but it has a high middle and it looks the same on either side and it has, somewhat equal length tails, so it's not skew one way or the other, they're about equal length, symmetric with a high middle, then you're allowed to use the empirical rule. And this is what the empirical rule says. Approximately 68% of the data will be within one standard deviation of the mean. Let's talk real quick about what that means. So this is the mean, so the average of the data. And if you take your standard deviation that you found, you add it to the mean, you get a number that's bigger than the mean. If you subtract the standard deviation from the mean, you get a number that's smaller than the mean. And what we're saying is, if you do that, you add it and subtract it to the mean, from the mean, then you can say that about 68% of your data should be between this number and that number, whatever those numbers are. So you know what mu is, you know what sigma is. You subtract sigma from mu, you add sigma to mu, and you have two numbers. You can say about 68% of the data is between those two numbers. And I'll show you an example in a sec. We can also say that approximately 75% of the data will be within two standard deviations of the mean. So if you subtract two standard deviations, or you add two standard deviations, whatever it is, then you can say that about 95% of the data is going to fall within two standard deviations of the mean, or between this number and that number, whatever they are. It's a really powerful thing. You can also say that almost all, or all of the data will be within three standard deviations of the mean. The number I saw for almost all is about 99.7% of the data. So just about that much, which is almost everything, will fall within three standard deviations of the mean. So you can do this. You can say sentences like these about your data if you have something bell-shaped. Now, one important thing to note is that the best you can do, even if it is bell-shaped, is to say this is approximate. So it's not exactly 68%, it's approximately 68%. Let's look at an example. So the following table represents the U.S. Census Bureau's projection for the percentage of the population age 65 or over for each state and the District of Columbia. So we have 51 measurements here, and if you look at our data, it looks about bell-shaped. Now you might say, well, that's not perfectly bell-shaped. Well, it's not, but it does have a high middle, and it does get low on either side, and neither one of the tails is that much longer than the other one. Like this one's a little bit longer, but not enough for us to really care. We're looking for a really long tail one way or the other, or a middle or a high part that's not in the middle. But anyway, so this is bell-shaped, which means we can use the empirical rule. To use the empirical rule, we need to find what mu is and what sigma is. Let's treat this like a population because we have a census and it's from all the states. So we're going to treat this like a population because it is. We found the population mean in the calculator if you put it in, and we could find the population standard deviation. And now we've got a bell curve that looks like the one on the last time. So what we saw was if it's bell-shaped, this is the mean. This is the mean plus one standard deviation. So if you take 13.31 and you add the standard deviation, which we just found, you get this number. If you take 13.31 and you subtract the standard deviation, you get this number. And once you do that, you got two numbers. So you got 11.54, which we found by taking this minus that. I'm sorry, that's 5.7. And 14.93, which you found taking this plus that. And now you can say that approximately 68% of the data is between 11.57 and 14.93. So you can say that because it's bell-shaped and because we found the mean and the standard deviation. It's really powerful, really powerful. You can also add 2 times the standard deviation to the mean, 2 sigma, or you could subtract 2 times the standard deviation from the mean. So 2 times that would be a little over 3.2. And when you do that, you get the numbers 9.88 and 6.61. So if you do 13.31 plus whatever double that is, you get 16.61. If you take 13.31 and subtract 2 of those, you get that. And you can say then approximately 95% of the data are between 9.88 and 16.61. Now you do it a third time, and you can say that almost all the data are between 8.2 and 18.3. So this is when you subtract 3 standard deviations and add 3 standard deviations. So you can say that. So what the empirical rule does is it lets you do this for any bell-shaped data set. So it's got to be bell-shaped. So you can't even use the empirical rule until you first make a histogram and decide that looks bell-shaped. And even if it is bell-shaped, the best you can do is say approximately. You can't say exactly, but it's still really helpful. It's a nice way to describe the spread of the data. You can tell me where most of the data is. This isn't very interesting, but you know, this might be interesting to someone, or this might be interesting to someone who doesn't know. So it's really nice. But remember that you can only use the empirical rule for bell-shaped data. There's also something called Chebyshev's inequality, which you don't need to have bell-shaped data for. This will actually work for any data set. So we're going to use Chebyshev's inequality for any data set. And this says that the proportion of data that are within k standard deviations of the mean is at least this number right here. So if this is 1 standard deviation from the mean, this would be 1 minus 1 or 0. That's not very interesting, but we'll set k equal to 2 or 3. If you set k equal to 2, this is 1 minus 1 over 4, which ends up being 3 over 4. So that's with k equal to 2. For k equal to 3, this is 1 minus 1 over 9, or 8 over 9. And that's that number right there. So what we can say then is at least 3/4 of the data are within 2 standard deviations of the mean. So that's with k equal to 2. And we can say that at least 9/8 of the data are within 3 standard deviations of the mean, which is not as powerful as the empirical rule, but it's still true. So we can't say exactly, we can say at least. So this is like approximately, it's not perfect. But we can still do it, and it's helpful even though it's not as nice as the empirical rule. So let's look at one of these real quick. We have, as part of a public health study, systolic blood pressure was measured for a large group of people, and the mean was 120 and the standard deviation was 10. And we want to use Chebyshev's inequality to talk about the data. Okay, so we have a sample mean of 120. Let me write it down like this. So we got the sample mean of 120, and we got the sample standard deviation as 10. So if I want to talk about things that are within 2 standard deviations of the mean, I'm going to do what's going on the left over here. So if I want to talk about things that are within 2 standard deviations of the mean, I'm going to take the mean, subtract 2 standard deviations. So you see if the standard deviation is 10, then 2 of those is going to be 2 times 10, or 20. So subtract 20, you get 100. If I take the mean and add 2 standard deviations, I get 140. Okay, so that's my x bar minus 2s, x bar plus 2s. If I want to do k equals 3 and talk about what's going on within 3 standard deviations of the mean, I'm going to take 120 and subtract 3 of these suckers, and I get 90. Or I can add 3 of these and get 150. And that's where those numbers come from. So it works just like the empirical rule when you get started. You're adding 2 standard deviations, or you're subtracting 3 standard deviations, and so on. Once you get those numbers, you can write some nice sentences. So this comes from the rule on the last slide, where it says at least 3/4. So this is the k equal 2 one. So this is when we're doing k equal 2. At least 3/4 had systolic blood pressure between 100 and 140. So this is like saying within 2 standard deviations from the mean. Which are those numbers? These are 2 standard deviations from the mean. This is the k equals 3 one. At least 8/9 had systolic blood pressures between 90 and 150. You could also say this is within 3 standard deviations from the mean. Sorry, PowerPoint's being frustrating to me. But this is how it works. So you can say sentences a lot like those empirical rule sentences. They're not as powerful. This isn't very interesting. You're saying like 90% of them are between this and this, which is probably not surprising. But saying 70% between this and this might be better. That's how you find it. You add 2 or you subtract 2 standard deviations. You add or subtract 3 standard deviations, and you get those boundary points. So there's 100, there's 140, there's 90, and there's 150. So that's Chebyshev's inequality. So remember, you can use Chebyshev's inequality for any data set, like this one, for instance. It's not bell-shaped. It's just ugly and not helpful looking. You can only use the empirical rule for something that's bell-shaped, but Chebyshev you can use for anything. There's that. Okay, let's talk about the last thing. So we can find something called a coefficient of variation, and it's not very hard to find. If you have the standard deviation and the mean, you can find it really easily. But what it does is it tells you how large the standard deviation is with respect to the mean, which is really helpful if you have data sets whose value have different units. So you don't usually just find the coefficient of variation, but if you have 2 different data sets, you may want to find the coefficient of variation, because what it does is it kind of standardizes this thing with respect to the mean and shows you how far away or what the spread's like with respect to the mean. So for instance, if one mean is like huge and another mean is small, then your standard deviation might be really big or really small. This will kind of relativize it so that you can see. Let me show you an example. The National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta, Georgia, had a mean of 49.8 inches with a standard deviation of 7.6 inches. And the annual temperature had a mean of 62.2 degrees Fahrenheit with a standard deviation of 1.13 degrees Fahrenheit. So we want to find the coefficient of variation for precipitation and for temperature. And then we want to talk about which one has a greater spread relative to its mean. So we're not asking which one has a greater spread overall. That would be easy. Which one has a bigger standard deviation? Well, this one has 7.6 inches. This has 1.3 degrees. But these are on 2 different scales. This is measuring distance. This is measuring temperature. I don't really care which one's bigger overall. I want to know which spread is bigger relative to its mean, so on its scale. So we can find the coefficient of variation by taking the standard deviation by the mean. So there's the standard deviation divided by the mean. We'll do it for temperature too, standard deviation divided by the mean. And this is my coefficient of variation. So these are 2 numbers. They don't have units to them. The units just cancel out. But this CV is 0.15. This CV is 0.02. And so now that they're standardized, they're not on any scale. This isn't in inches anymore, and this isn't in temperature. They're just standardized. They're just numbers. So I can say the CV for precipitation is larger than the CV for temperature, just because that's bigger than that. That's how I get that. Therefore, precipitation has a greater spread relative to its mean. It also had a greater spread overall, but now that you've taken the units away, it's got a greater spread relative to its mean. So that's a nice way of comparing 2 data sets that are not on the same scale and have different units, and you can describe one spread with respect to the other. We couldn't compare inches to degrees. That's apples to oranges. But I can compare them once I divide out the means, and I can say, oh yeah, that's definitely bigger than that. That's much more spread out with respect to its mean than that one. So that's another helpful thing. So all 3 of these things are kind of nice ways of talking about the spread. A lot of people, and you may not, if you're new to statistics, aren't really comfortable even talking about what a standard deviation is. It's just some number that we found, and I don't really know what it means, but the stuff in this video are much nicer things to say that a lot of people can get their head around. Like, 75% of the data is between here and here. Like, you can understand that a lot better than, oh, the standard deviation is 5 minutes. What does that mean? So I suggest really trying to get your head around this part of the section, because this is going to be really helpful as far as communicating the kinds of things you're going to be doing with data in the future.